Welcome and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's call. At that time, you may press star 1 to ask a question. I would now like to turn the call over to Mr. Fred Rank. Sir, you may begin.
Good morning, everyone. I'm Fred Rank, Safety Engineer with FHWA's Resource Center. I'll be the presenter for this morning's webinar on the HSM application series. This morning's webinar will be on project identification and screening using the Highway Safety Manual. In getting started this morning, I would first ask all of you who are on the audio connection and participating, if you could participate in the poll in the upper right as to the number of people who are on your call-in line, who are logged in on connecting to this webinar. This helps us determine roughly, and it's surely not very exact, but roughly how many people are participating in today's webinar. I'm now going to also call your attention to, on the right-hand side, the pod that's got HSM webinar series presentations. You will notice that in this pod are each of the three separate PowerPoints for this morning's presentations in this webinar. And additionally, there is I want to call your attention to the HSM primer that's right at the bottom of the pod. That's a very helpful tool that provides more information on screening and how to use the Highway Safety Manual for screening. There's some excellent detailed examples in that primer that was developed by FHWA and AASHTO, and I would urge you to download the presentations as your working copy of the Highway Safety Manual until at such time the printed copy arrives from AASHTO that you'll be able to use. And this file share pod will be made available at the end of today's webinar and left up in this room, so it'll be available to you to do downloads after today's presentation. At this point in time, I'm going to switch us over to the presentation room, and we will begin today's webinar. What you should see now coming up on your screens is the loading of the PowerPoint presentation. And your very first slide you should see is that our overall opening slide, the Highway Safety Manual Webinar Application Series, and this one being the HSM applications to project identification. This is the fourth in a series of 12 HSM application webinars. We started these last week with our HSM introduction and application to two-lane rural roads. On Tuesday, we conducted the HSM applications to urban-suburban intersections. And today's project identification using the HSM is going to build on last week, on Thursday's applications to two-lane rural roads and Tuesday's applications to urban-suburban intersections in the examples to illustrate how to use, that will be illustrating to you today on how to apply the HSM to identify projects. Additionally, when we conclude the entire series of 12 webinars, we anticipate that we will be scheduling and putting on additional webinars on HSM applications and additional examples and case studies to help those of you who are interested in the Highway Safety Manual start using the Highway Safety Manual and putting it to work in your projects. The very first session of the day in this morning's webinar on applications to project identification is some general background and information on highway safety overall. I'm Fred Rank. I'm a safety engineer with FHWA's Resource Center. Our outcomes in this first module that we will cover are to review the safety performance of U.S. highways and streets and to define substantive safety beyond what you may have known as nominal safety in your work as a transportation professional. Overall, in the United States, we have a significant number of states that have more than 850 traffic fatalities a year. The states shown in blue have more than 850. Those in red range between 300 and 850, and those in green have less than 300 traffic fatalities a year. Our fatality rate has dropped significantly in 2008 and through 2009. The data available from NHTSA and the FARS files from 2008 indicate a 9.7% drop in the fatality rate per 100 million vehicle miles of traveled. We are now down to an all-time low for many, many decades in terms of traffic fatalities. Most of this can be tied or linked in some way to the recession and our current low level of economic activity, but we're starting to recover, and I'm hoping, all of us are hoping, that we do not see a rise back in traffic fatalities, crashes, and injuries. If our rate that we're down to now of 1.25 would continue, we would be between the upper two trend lines. We certainly don't want to be at that upper line of 1.41. Even at a rate of 1.0, which we're at 1.25 now, we would still be at a result in 48,000 traffic fatalities a year in the year 2030. That's unacceptable, and it's too large. And hence, safety is an important issue. It's something that we're going to continue to have to work hard at. And the Highway Safety Manual offers us to be able to use technology, to use knowledge as a tool to do a better job in our safety programs. Some things for you to keep in mind. It highlighted for fatal crashes in this table is the rate for two-lane rural highways being the highest of the roadway classifications in terms of fatalities. Injury crashes is both four-lane undivided and also total crashes, four-lane undivided. Many of us in the highway profession, the highway engineering profession, transportation engineering, have known for a long time that adding two lanes to a two-lane highway to make four doesn't necessarily make for the best operational design or safety performance design. And the rates for injury crashes and total crashes clearly show this to be the case for undivided multi-lane highways. Some other information for you to know is the issue of the rural non-interstate in terms of fatality rates. Rural continues to be one of our biggest challenges that we have. Roadway departure, of the 34,000 fatal crashes, nearly 18,000 are associated with roadway departure. And running off the road and crossovers continue to be a big issue. Overall, in fatalities, roadway departure crashes constitute more than half. In terms of horizontal curves, which are a portion of run off the road, I've shown you a slide depicting each of the states in the United States in terms of the number of fatalities for horizontal curves. You can see that some of the bigger number states are Tennessee, Missouri, Washington State, Colorado. Approximately 28% of fatal crashes overall occur along horizontal curves. The crash rate for horizontal curves is about 3 times that of the tangent segments. Intersections are a small part of the overall highway system, but they constitute about 1 out of every 5 traffic fatality, but they account for more than half of all reported crashes. If we look at total crashes and also fatal and injury crashes, intersections, whether they're stop-controlled, intersection signalized, constitute about 55% of all crashes. When you combine fatals with injury crashes, it's even slightly higher. Although they're only 21% being total crashes or fatals, overall, intersections have the largest share of total crashes. Some key things for you as the transportation professional to keep in mind. As much as we know today, our knowledge continues to be somewhat imprecise. Exercising judgment based on your professional experience continues to be the most essential part of the practice of transportation engineering. Just because you satisfy the nominal requirements of a state's design standard or national design standards doesn't necessarily make a highway safe. Some important features of highways and transportation design are not determined by standards. Such things as spiral transitions to horizontal curves, center two-way left turn lanes. Horizontal curves continue to be a real challenge for us in the United States. Fatalities at 28% are even more than the 21% of fatalities at intersections. Transportation engineering as we know it today has been changed significantly. 20 years ago, we thought of safety being inherent as long as we met the standards for design, for operation, as set forth in the geometric design policy by AASHTO, known as the Green Book, or in the Manual on Uniform Traffic Control Devices, which applies nationwide. In the mid-1990s, a new way of looking at safety and safety performance was created, and that is looking at the subsidy safety performance, and which is the actual number of crashes for a piece of highway or for an intersection. And this differs and goes beyond. Nominal safety was based on research and experience, provided a consistent level of quality, typically was associated with overall cost effectiveness. Today, we would think of nominal safety as the first step. Do the elements in our project in our location comply with what we have for our design standards for highways, for intersections today? To give you an example, nominally, a highway curve with normal super elevation transition to 6%, we think of that as producing a safe performance. What we know today from research, which is set forth well in the Highway Safety Manual, is if we use a spiral transition in combination with the super elevation transition, we will have 12% fewer crashes. It's not a constant value. It does vary by the amount of exposure of the road and the degree of curve, but in general, about a 12% reduction in crashes. The Highway Safety Manual, a new document, many years in the making, allow us to quantify something that we've struggled with for a long time. We can quantify environmental impacts. We can certainly quantify operational analysis using the methods, the procedures, the software of the Highway Capacity Manual. We can do an economic analysis of design alternatives. But with the Highway Safety Manual, we're finally going to be able to address what's the safety impact and quantify it in terms of crash frequency and changes in crash frequency. The methodology of the new Highway Safety Manual is like that of the Highway Capacity Manual that is used to assess and assure adequacy of capacity. The Highway Safety Manual will allow the transportation professional to understand and to quantify crash frequency performance for informed and balanced decision making. And that is quite an achievement. And it is, I see it as a major change and advancement in our profession of transportation engineering. The Highway Safety Manual is like the HCM. It describes the mathematical relationships in terms of equations for performance, for crash frequency performance, that is, based on exposure and site conditions. It's an analysis tool, and an analysis tool only, just like the Highway Capacity Manual is. It doesn't have standards in it. It does not have best practice guidance. The Green Book and the MUTCD are standards and guidance for transportation engineering across the country. These are standards and guidance. The Highway Capacity Manual is not like the Green Book. It's not like the MUTCD. It is only a set of mathematical relationships for analysis of crash frequency performance. So the HSM, the Highway Safety Manual, is a set of tools for analysis. First of all, it'll allow us to predict crash frequency, and then we can use it to analyze safety options and countermeasures, to provide the analytical tools to predict the impacts of decisions that affect crash frequency performance. facilitate our consideration of safety measures and countermeasures throughout the project development process. And it really is the best synthesis of the validated highway safety research available to any practitioner. So the new Highway Safety Manual, how can you use it? You can use it at the program level to prioritize segments within your overall highway system or for specific locations. At the project level to assess, quantify just what are the safety needs that need to be addressed in the project, communicate those needs to the public in a clear and reasonable way, prioritize the decisions and the portions of that project and the things that will affect its performance to keep it within the budget. And if used properly, you could use this, and I do see that it will be, to demonstrate that your proficiency in quantifying safety needs and addressing them in any project. I do need to make you aware that FHWA issued a program memorandum supporting the inclusion of and consideration of safety in all aspects of a project back in January of 2005. Considered in every aspect for planning and programming of projects, in the environmental analysis, in the design, construction, maintenance, and in the operations of the project. So with the Highway Safety Manual, we'll be able to quantify the different safety performances of various alternatives, including the no-build, and with that quantification, be able to include it in the overall decision-making in the project. So in this first session, we've covered how design, the role of roadway design, and application of standards can achieve meeting the nominal requirements, that is, those that are in name only. We know that in the design, we can affect the incidence of human error. We know that with the design of a transportation facility, we do affect and change the chance of a human error resulting in a crash, as well as the severity of the crash. The human being in the driving task makes mistakes, and the error rate of the human being in the driving task is well known. Human beings make errors on a recurring basis each and every moment of driving. It's inherent in the process of the human brain being a parallel processor that's starting with the appropriate input conditions, the things they see, sounds, that feedback that they're getting from the car and what they see, they make choices. But in a parallel processor, the branching to a correct decision isn't always the same path or to the same outcome, and hence the inherent error rate associated with the human being in the driving task. How we as transportation professionals engineer, design, operate, and build our projects does affect will that error on the part of the human being driver result in a crash and the severity of that crash. So the Highway Safety Manual, what can it do for you? Well, we can use the Highway Safety Manual to predict the safety performance of geometric design features. When I say safety performance, I mean crash frequency and reducing crash frequency. We can use it to quantitatively calculate a safety effect, that is, effect of crash frequency. We can use it to predict the safety performance of intersections. All of these we can answer definitely yes. And these are welcome, new, proven methods that we can use as a transportation professional so we can have better decisions for safety. So in this first session, we've covered this overall safety performance of U.S. highways and how that as much as we like to think we've advanced and changed, we're still a lot like dealing with the same issues of those that came before us as transportation engineers 50, 60 years ago. In the night after World War II, the practice of highway engineering, if you took care of the approaches of narrow bridges, of intersections and sharp curves in a project, you probably satisfied most of the need in a project. And in some ways, to a lot of ways, it's still true today. We struggle with having safe intersections, with having safe operating sharp curves, and approaches to narrow bridges. Also, in this first session, we described to you subsidy safety going beyond nominal safety, a further approach, further aspect of our profession of transportation engineering. I'm not going to take questions at this point in time. We are going to hold the questions until we complete the technical presentations. Next, I want to cover the use of the Highway Safety Manual in identifying projects. This morning, the material that I'm going to make use of is to build upon what has already been covered in our previous sessions of Tuesday and last Thursday on the Highway Safety Manual for two-lane rural roads and for multi-lane urban intersections. And the question that I'll pose to you in the beginning of this session on is this the photo, what you see in the photograph on this cover slide, is this a higher crash location? And I will tell you that in this case, the location in it was. To the end, there was a crash involving an overturned school bus and another serious crash at this location. It's a T road off to the left. It's an older vertical profile state highway originally built in the 1920s. We're going to apply the Highway Safety Manual to specific sites and situations, and we're going to compare the predicted crash frequency using the Highway Safety Manual and its techniques to the actual crash performance, which is the subsidy crash frequency performance for these sites. AASHTO, which is publishing the Highway Safety Manual, has not been able to get to us the final exhibit numbers and the final, as published, page images for the new Highway Safety Manual. So until that time, the exhibit numbers that you'll see in today's presentation, as in the ones previously, aren't going to maybe be the same numbers as what you will see in the published final copy. The material, the values that are in the exhibits, the equations, the coefficients will be the same. Additionally, the term AMF, or accident modification factor, was changed by AASHTO to be crash modification factor, a much better term to clear up this aspect, and that is how it's going to be published in the final HSM. So, to get us started on applying the HSM to determine or to identify a higher crash location, let's start with a very typical thing that happens in public agencies with highways. Telephone call from a citizen asks for action to make improvements to an intersection. The intersection is unsafe in the view of the person, and there are lots of crashes. To field this request, we typically would have gathered information and a quick check for this one. The district crash summary identified 8 crashes in 3 years. The location was not on the district's 5% list, nor on a high crash location list for the district. At this point, doesn't seem to be much of an issue. In doing a numerical determination of crash rate for the location, and we're looking at 8 crashes in 3 years. Our average daily traffic values for the state highway to through route are about 5,000 vehicles a day, about 1,200 on the side road. We calculate a crash rate of about 1.18 crashes per million entering vehicles. In comparing this to the averages for the state, for larger areas, for yield or stop controlled intersections, a typical crash rate of about 1.08 is very typical, not that unusual, or less, slightly less than 1. So our value of 1.18 for crash rate would be just above our typical crash rate for the area, for that state or group of states. So there doesn't seem to be much of an issue here. Let's take a look and see how we would analyze this using the methods, the known knowledge of the new Highway Safety Manual. In last Thursday's webinar, we covered two-lane rural roads and intersections of two-lane rural highways, and we introduced you to a safety performance function for a three-leg stop-controlled intersection in which the stop sign faces the stem of the T. EXP is natural E, LN is natural log, ADT of the major road would be the larger of the ADT values, and the ADT minor is the smaller of the two. For 5,000 on ADT on the major state highway and for 1,200 on the minor, the calculated value would be about 1.4 crashes per year, or about 4.25 crashes in a 3-year period. Wait a minute. Wouldn't the actual number of crashes higher than this? So there are locations of side road approach to a marked state route. Using the traditional way of doing business and looking at intersections, we found 8 crashes in 3 years. Our crash rate's about 1.18. But with the Highway Safety Manual, in this first step, and we're going to do it another step addition, but it's just as a first cut, our predicted crash frequency is about 1.4 crashes per year. But we had actually 8 crashes in 3 years, which is about 2.7 crashes. So using the Highway Safety Manual, it's the actual number of crashes. The substitute safety performance is about 90% greater than the predicted crashes. That's certainly not how we would have looked at it in terms of crash rate in comparison, comparing crash rates. The Highway Safety Manual and putting together large data sets across multiple states that are very representative of the experience across the whole United States. Minnesota, North Carolina, California, Texas, Illinois data sets in the intersection safety database have defined a series of curves based on the ADT of the major road and the minor road as a function of crash frequency. The problem with crash rate is it will give us a value for an average rate across all ranges of ADT. And inherent in that is sort of its shortcoming of looking at things the way we traditionally have. An intersection whose performance is below the curves, not the average rate line, probably we don't need to be concerned with. But an intersection that has this much frequency in terms of crashes as a function of its exposure or ADT values certainly is above the curve line. Although the end of the arrow at the bottom points close to where the average rate would be, really what it is I'm illustrating to you here is it's to the representative curve for the relationship of ADT major, ADT minor to crash rate. And the difference between that curve and our actual number of crashes, I'm going to identify to you as difference. And I'm doing this at an elemental level and not getting into empirical Bayes methodology to adjust for regression to the mean. That is well covered, and we're going to cover this in detail in the following session to describe to you how that works using the Highway Safety Manual. This is a first step, and in the second step, we'll apply the CMFs, or crash modification factors, to allow us to adjust our predicted crash frequency value for the actual site conditions. In this case, we had a 3-leg intersection in which one approach has a left turn lane. So we would take our calculated predicted number for crash frequency of 1.4, multiplied by the CMF, and our predicted value as adjusted would be about 0.8 crashes per year. We were experiencing our substantive safety performance of 2.7. So now we have 2 very important pieces of information in hand. From a simple calculation, we now know we have a starting point. The predicted crash frequency for the typical intersection in this database put together of nationally the most intersections to analyze to develop the relationship. would have given us a crash performance of about 0.8 crashes per year. That's our starting point. The measure of the difference is the difference between our regression line curve, and we were above it, of 2.7 crashes per year. We have a difference of about 1.9 crashes per year. Now, this is just elemental level. This has not been adjusted empirical Bayes methodology to determine something called excess crashes. We'll get to that. But I wanted to give you this information to show you the methodology, the strength of the Highway Safety Manual. We'd have a situation in which we had an intersection. The number of crash rate was not that much above the norm. It wasn't on the district's 5% list or high crash locations, but it is operating a lot higher. Its subsidy safety number of crashes is significantly higher than what the predicted value would be for all of the crashes across the country in the largest databases we could put together. So this location, our traditional approach would be not much going on here, but our Highway Safety Manual says, wow, we have a subsidy safety performance nearly triple that of the predicted crash frequency for this location. That puts things in a very, very different light. And it is something that is the intended result. This is exactly what we wanted to have the safety analysis tools to be able to do, is to look at intersections and not just those at the top of the list on frequency alone. So this is a higher crash location, in fact. And we probably wouldn't have known that, except we now have the new technology to be able to do it as found in the Highway Safety Manual. Let me give you another example. Building on Tuesday's webinar for multi-lane urban-suburban intersections. This is a intersection, skewed, signalized, outside of, it's in the Chicagoland area. It's on a major arterial, and it averaged about 12 to 15 crashes a year. Locations was not on the city's top 25 list, in which many of those intersections had 30 to 50 crashes a year or more. So this wasn't on a list and had never been for a number of years. It's a four-approach signalized intersection with 28,000 ADT on the major road, 5,500 on the minor. Skewed about 40 degrees. We have left turn lanes on the major and minor road approaches. We have protected permissive left turn phases, lighting, and right turn on red is allowed. No right turn lanes, and there was no speed enforcement cameras or red light running cameras at this location. So using the Highway Safety Manual and its predictive equations for this ADT level for the 4SG model, our multi-vehicle crashes, and we do that as the first of two calculations to make of crash frequencies, results in a value of about 7.1 crashes, 7.01. For single vehicle crashes, and that's the other group of collision types at a signalized or stop-controlled intersection that is multi-lane. It's a different set of coefficients for A, B, and C, about 0.4 of a crash per year. We add these two together to get our predicted crash frequency for the intersection. Now this is the first step, predicting the crash frequency. The next, using the Highway Safety Manual, and it's an interesting outcome because we've got 12 to 15 crashes a year. So very first thing before we adjust for actual site conditions is this intersection has about double the number of crashes, or more than double the number of crashes that typically we should see for this kind of ADT values for a signalized intersection. In fact, here's the curves, the average crash rate. We're on one of these curves that start from zero and slope up and to the right for the side road ADTs, and probably the one that would be the closest would be the upper of the curves. We're not down here below the curve. We're above it up here. And the difference is not to, again, the bottom of the arrow isn't pointing to average rate. It's pointing to that upper curve. And that amount of difference is fairly large for this location. So adjusting for actual site conditions would be the next step to adjust our crash frequency prediction. We want to adjust for left turn lanes on all 4 approaches, and we pull that CMF straight out of the table. And this is Exhibit 1241, and you notice that it identifies this as AMF, and we know in the final Highway Safety Manual it will be CMF. And that exhibit number may change, like it may be 1239 or 1252, but the values in it, that 0.66 for CMF will not change. For left turn phasing, we have 1.00 for permissive turns, 0.99 for protected permissives, and it's operating as protected permissive. So we need to multiply the values in this case because it's operating protected permissive on all 4 approaches. And our CMF for the type of left turn phasing would be 0.96. There are no right turn lanes, so our CMF is of essentially the base conditions, or 1.00. The right turn on red is not prohibited. There are no approaches for this where this is posted or this is regulated. So our CMF is 1.00. Lighting is present for the intersection, and our value using one of the exhibit tables for a signalized intersection, multi-lane, would result in a CMF of 0.9107. So, using the Highway Safety Manual approach, our crash frequency predicted was 7.41, and then we would multiply the CMS for left turn lanes, for left turn type of phasing. There is no right turn lanes. There is no turn on red. No turn on red is not posted for any of the approaches. We do have lighting, and we don't have any red light cameras. So the resulting effect is about a predicted crash frequency of about 4.4 crashes per year. Our subsidy safety performance was about 15 a year. So in fact, this intersection was operating and resulting in about 4 times the number of crashes as one would predict with the Highway Safety Manual. Now, I have not used empirical base to go back and look at the crash performance. I'm only showing you as simply 15 crashes a year as the crash record, rather than going back and adjusting for random. And I'm doing that so we don't end up with 30 slides of math up here to get to the point of how to use the Highway Safety Manual. So this is definitely a higher crash location. In fact, even though it didn't show up on the city's top 25 list, and it didn't show up on any list in terms of rate. All right, a next location. Let's look at a rural 2-lane highway curve, building on a week ago session on 2-lane rural highways. This curve up in Michigan's UP has 4 crashes in 2 years. This is a 2-lane rural highway. It's been identified as having a crash rate much higher than a statewide average. Our segment of roadway is short in length. We have the traffic value, 11-foot lanes, no shoulders, roadside hazard rating is 3, driveway density is 5 per mile, no left turn lanes or passing lanes. Our radius is 600 feet, and our super conforms to the Green Book policy. No spiral transition was found. So our first step is we would predict the crash frequency for the segment of 316 feet long based on its ADT in miles, and that predicted value is 0.16 crashes per year. Now we had 4 crashes in 2 years, and I'm looking here at a predicted crash frequency of 0.16. At this point, I want to call your attention to a very important thing, and you're first starting to use the Highway Safety Manual to calculate values. For the most part, your experience as a transportation professional is going to have been jaded. You have been asked to look at and to deal with high crash locations and to make engineering improvements to high crash locations for the majority of your professional life. The Highway Safety Manual is for all intersections and all curves and all pieces of roadway. And the representative values of the regression line as a function of ADT, is the middle of that entire data set of performance. And it isn't focused on the only on those upper high crash locations. So the values, when you calculate them, will always seem rather small. Many users, first-time users of the Highway Safety Manual, will make a calculation and then say, my gosh, I've done something wrong. Where did I go wrong? How? This number is small. And this is not an untypical answer. In fact, performance of our entire highway system is not so adverse. It's just that we, the transportation professionals, end up having to deal with mostly high crash locations in our projects. We would then adjust for the specific conditions for lane width, and we have 11-foot lanes rather than 12s. And we would need to adjust this to the proportion of cross-section related crashes. The Highway Safety Manual is primarily focused on total crashes. And we know that run-off-the-road crashes, head-on and side swipes, only constitute about 57.4% of all total crashes. So we need to adjust this by our percentage of related crashes. So our 1.05% is really an effect of about 2.9% when adjusted to total crashes. For shoulder width, we have no shoulders. So we adjust that value of 1.5 by our 57.4 cross-section related crashes. And if that distribution is different in your area based on your knowledge of your highway system, then use your area's value for the percentage of related crashes. We would then add it, we would multiply the net effects of shoulder width and lane width by our predicted crash frequency of 0.16, and we get a value of about 0.217, or about 1 every 5 years. Now, this segment is a curve. Our third step is to develop the CMF value for horizontal curves. And it's a function of the length of the curve in miles, the radius or R of the curve in feet, the presence or S of a spiral transition, and our calculation in this case are for our curve length, 316 feet, 600-foot radius, rather small, sharp curve, is a CMF value of about 2.44. That is, this condition of this curve would result in 2.441 more crashes than if this was a tangent piece of roadway of that lane width, no shoulder width, and other factors. That's a significant effect. And in fact, you'll remember in my introductory comments that typically horizontal curves have about 3 times the number of crashes as if they were a straight segment. So we'll apply our 2.441 times our predicted crash frequency adjusted for lane width and shoulder width, and we get a net effect of about 0.53 crashes, or 1 every 2 years. Our substantive crash frequency was 4 in 2 years, or 2 per year. So in fact, this curve has nearly 4 times the predicted crash frequency, and we would probably identify it as a higher crash location. Just looking at it, you might not have known that. The beauty, the strength, the value of the Highway Safety Manual is to give you, the transportation professional, a very solid determination as to, is this location a problem or is it just the norm? Are we above the regression line for this amount of exposure and site conditions, or are we below it? In this case, we're essentially 4 times what the predicted value would be. So in the second session, we've applied the Highway Safety Manual to 2-lane rural highway intersections, to suburban multi-lane signalized intersection, and to a rural highway curve, all based on the technology of the Highway Safety Manual as we set forth in the previous webinars. And we've compared the predicted crash frequency to the substantive crash frequency for the same location, and that substantive crash frequency is actual crashes, to identify, is this location a higher crash location than the norm? the third session, we're going to jump beyond the elemental level. And now that we've covered the basics and how the Highway Safety Manual can help you, the transportation professional, do a better job in understanding the crash frequency performance of your project that may be of segments or intersections. We're going to apply the Highway Safety Manual methodology and its models to candidate segments and curves and intersections and compare it to the substantive safety performance to identify the higher crash locations. Part B, and there are 4 parts to the Highway Safety Manual, as you learned in the first session, the overview. Part B, it consists of 6 chapters, and the first is Chapter 4 on network screening, 5 on diagnosis, 6 on countermeasure selection, economic appraisal, and prioritization of improvements are 7 and 8, and then the evaluation of the effectiveness of the measures that you have included in projects by your agency is covered in Chapter 9. But Chapter 4 is network screening to identify locations of higher crash frequency. And Chapter 4 is in these we can identify using the Highway Safety Manual methodology. We can identify and rank these sites within our network to program improvements to reduce crash frequency. So we can use it to identify the sites, those that have a substantive crash record, a crash frequency greater than what we would predict with the Highway Safety Manual to the middle, that regression line to the middle of the data set for all locations of that type. We can use it to identify contributing factors to crashes. One of the beauties and strengths that I've found in applying the Highway Safety Manual is when a crash frequency, a substantive crash frequency, is found to be way above the norm. As you start digging into it and analyzing it, the various aspects of collision types, whether they're right angle, rear end, or the nature of the rollover or the roadway departure crash, can point you directly back to where the root causes are, and then you can select the appropriate countermeasures. An additional real strength of the Highway Safety Manual is in assisting you, the professional, to identify the contributing factors to crashes. Most importantly, you can calculate the safety improvement of various design alternatives and how they would perform by predicting the crash frequency with that countermeasure in place. So you can use the HSM to predict the safety performance of a facility that does not exist. You can use it to analyze the crash frequency performance of an existing facility, the no-build alternative that is, and you can estimate potential crash frequencies on highways in general. Do more than just estimate. You can calculate the potential effects of crash frequency reduction in your decisions in a project. So here's a simple example, and I'll take this at the elemental level, to identify those locations with the largest difference of actual crash frequency, that's substantive safety performance that is, in comparison to the predicted crash frequency. Now this is not an empirical Bayes example that I'm going to use in which we account for regression to the mean. Let's just take this as a simple approach at the elemental level. We're going to look at those locations, identify a group of intersections, and to select the one with the largest difference. So if we have 3 locations, and we have crashes, our total crashes over a 3-year period, we have one location, number 1, with 28 crashes a year, number 2 with 25 crashes a year, and number 3 with 8 crashes a year. They vary from the number of approaches and by the type of signal or stop control, whether they're urban or rural. And that would be very typical of your experience in a district of a state. You'll have intersections that vary by urban and rural, by whether they're signal or stop controlled. The ADTs will range probably greatly. In this case, intersection number 1 and number 2 are very, very busy. Total ADT for that first intersection is 48,000. It's 48,000 for the second intersection. and a total ADT on the intersection number 3 is only 13,500. And with this great range of conditions, in there lies the complexity of how do we compare normative crash performance. When do we know when an intersection is a higher crash location that we need to look at in detail? So if we looked at it in terms of total crash frequency, we'd probably select intersection number 1 or intersection number 2. With 84 crashes or with 75 crashes, those are large numbers. Get back to where we were. So if we rank by the number of crashes per year, we would put intersection number 1 at the top and at 28 crashes a year. If we ranked them by terms of rate per million entering vehicles, why intersection number 3 is the largest, but just slightly above that of intersection number 1. If we look at predicted crash frequency using the Highway Safety Manual, and we make our prediction of the number of crashes per year, the highest value is 10.92 for intersection number 2. So as we're moving forward and looking at just three intersections here, we've had intersection number 1 with the most crashes, intersection number 3 with the lowest traffic. We've got a range of things, and how do we look at it all together at one time? If we look at the difference from the predicted average number of crashes to the actual number of crashes, it turns out that intersection number 1 has the largest difference, followed by intersection number 2. And I would like to suggest to you that maybe a different way of looking things are to look at those intersections that have the greatest difference from the predicted crash frequency in terms of their safety performance as a way of better identifying the intersections with the most need, and not just in terms of total crashes, which also in this case happen to be intersection number 1. So at the elemental level, and we haven't accounted for regression to the mean and our crashes over this 3-year period, but just at the elemental level, and using the term difference for between actual and predicted number of crashes, intersection number 1 probably would go to the top of our list. It's the highest on frequency. It's almost the highest in terms of rate, and it has the greatest difference from predicted crash frequency. Part B includes in Chapter 4, includes a lot of information about the empirical Bayes method to identify those locations with the largest excess crashes to predicted crash frequency. This information is well illustrated and described in a publication that was recently developed. It's called A Primer for the Highway Safety Manual, with the title of An Introduction to the Highway Safety Manual. It's a product of AASHTO and FHWA. I've included this in the file share pod so you can download it at the end of today's session. Part B, Chapter 4, describes in detail the empirical Bayes method, and it suggests the steps to monitor and reduce crash frequency and severity on existing roadway networks. The chapters in Part B are network screening, diagnosis through Chapter 9 on safety effectiveness evaluation. And network screening, Chapter 4, relates to diagnosis, to selection of countermeasures, to economic appraisal, to prioritization of projects, and then what did we actually get for the improvements we made, and how that evaluation is properly, with statistical rigor, conducted to evaluate. And then back using that same information and using it in your network screening of your agency in terms of crashes. So Part B, Chapter 4. Includes an example application illustrating network screening process. And within it, they depict, they illustrate, they provide an example of applying the empirical Bayes adjustment method to account for regression to the mean when you have more than 1 year of crash experience. The examples I provided up to this point to you have all been just simple for illustrative purposes of the methods. Now it's going to get a little more difficult. And hence, screening tends to be done at the large agency, usually at the state level. With your empirical Bayes adjustment, each site's evaluated as a function of how much the predicted crash frequency differs from the long-term empirical Bayes adjusted average crash frequency. This is identified not as difference, but as excess value, and it's a term that's used in the Highway Safety Manual. Sites with excess value are most likely to respond to safety improvements because they are theoretically experiencing more crashes than other similar sites for the same ADT and other conditions. Now that's good to know that a safety improvement for which we have a known CMF, we apply it to a high crash location, we can anticipate seeing a sizable, noticeable improvement in crash frequency reduction. Hence, those things that we've called in the past CRFs, or crash reduction factors, largely were developed as percentage crash reduction, largely were developed from information on high crash location remediation. And those values tend to be higher than our CMF values that we're saying you will get this reduction in crashes when you apply it to all sites at this ADT exposure and conditions. An advantage in the EB method to identify those locations that have excess number of crashes is you can use it as a performance measure to evaluate a mix of intersection types, curves, segments, and traffic volumes in an even-handed, statistically valid, rigorous process. So the basic procedure, as detailed in the HSM primer, is for each site, you calculate the predicted average crash frequency using the methods and predicted formulas in Part C. In Part C, remember the Highway Safety Manual is chapters 10, 11, and 12. 10 on two-lane rural highways, 11 on rural multi-lane, and 12 for suburban urban multi-lane. For each site, calculate the expected average crash frequency using EB, empirical Bayes methodology, from Part C appendix of the Highway Safety Manual, and then you calculate, they call it an estimate of the excess value, in which you subtract your predicted value from the expected value. And your excess is the difference. In this case, in the example, they have separated fatal injury crashes from property damage crashes, and that's why you see the subscripts of PDO for property damage and FI for fatal injury crashes. And done these independently using the coefficients in the crash prediction models associated with PDO crashes and with fatal injury crashes. And the example for intersection number 1 is in excess of 1.5 crashes. And this is from Table 4 of the Highway Safety Manual primer. Our intersection had an observed crash frequency for fatal and injury of 2.8 a year, 3.4 for property damage only. We predicted, say, SPF, a safety performance function, for fatal and injury of 0.5, 0.9 for PDO. Our EB adjusted average crash frequency for fatal and injury is 1.2. Our EB adjusted expected average crash frequency PDOs is 1.7. Our excess is 1.5 crashes a year. But the observed fatal and injury in PDO was a total of 6.2 crashes per year, comprised of the 2.8 plus the 3.4. So that excess value with adjustment for random occurrences is a way of looking rigorously mathematically at a large number of intersections to identify those that have the highest excess. And if you look down the list of the right-hand column of Table 4, The values range in this case between 3-leg signalized urban, 4-leg urban signalized, but the excess values range between 0.03 all the way up to 2.22 for intersection number 6, which is a 3-leg signalized intersection. The value of the HSM is you can program these, do them in spreadsheets or any other way you want to do it with your database you have for your state's intersections or curves or segments, and screen to identify those locations that have the largest ordinate or magnitude value for excess as a list of locations for further study. And in fact, Table 5 is the ranking of the intersections that shows intersection number 6 having the largest amount of excess crashes above the expected value. The difference between the substantive actual number of crashes and the expected number of crashes based on our adjustments to our predicted crash frequency with AMFs applied. So the results of this screening is we can produce a final ranking, in this case of intersections, to determine which ones have the highest amount of excess crashes, and in this case we identified intersection number 6 with 2.22. So in this third segment, we've described in a minimal way, just a cursory overview, how to use the HSM methodology in a rigorous manner to screen all intersections, all curves, all segments in your area, in your jurisdiction, to identify those that have the largest ordinate value for excess crashes. That is, the subsidy safety record number of crashes, and then subtract the predicted crash frequencies adjusted for site conditions. And this can give you a very interesting list of higher crash locations for which have the potential to, you can program improvements to reduce crashes. And at this point, if I could ask Chase to open up the phone lines, we'll be glad to take, first, I'd like to take audio questions from those of you in the webinar as to the material and the information in this webinar, and then I'll go to the chat bot and work through the questions as time permits. So Chase, if you'd be so kind to ask for those who have questions, and we'll go work, we'll be glad to try and help you with answer your questions while we're in the webinar today.
Thank you. We will now begin the question and answer session of today's call. At this time, if you'd like to ask a question, please press star 1 on your touch-tone phone and record your name clearly when prompted. Your name is required to introduce your question, so please check your mute feature. Once again, star 1 to ask a question. One moment, please, for the first question.
Chase, if we have no questions at this point, let me start working through the chat pod, unless you have a question that you're handling.
It looks like I have no questions at this time. Once again, star 1 to ask a question.
Okay, thanks, Chase. Let me take the question from the beginning that Jason posed. I'll start working through them and try to answer them as best as I can during this webinar. Jason Osmond, given the same signalized intersection, but one designed with standard shoulders and a narrow raised median island, and the other is designed with 5-foot shoulders and a wider raised median island, will the HSM predict which geometric features perform better? And the answer is yes. And they'll be able to do it in a very good quantitative manner, and that is through the extensive number of crash modification factors available for intersections and for multi-lane segments. The HSM primarily is devoted for analysis of geometric features. The portion that is the thinnest that there is probably the least material are the other aspects of traffic control and non-geometric features. In Montana Division, please clarify the calculation of intersection crash rate. I'll be glad to. The crash rate, we want the total entering number of crashes. For ADTs of 5,000 and then 5,000 on another leg and 1,200 on the T, to get the entering volume, we're going to make the assumption that the entering volume is half of the total daily traffic for each of those three approaches to the intersection. The 5,000 value would be used by the HSM is used in an entirely different way. The HSM was purposely set up, organized, structured, so that you needed only the simplest of traffic exposure values, and that is the ADT for the two intersecting roads. It is not the same as what we've calculated. It's a different equation. It works differently. The HSM, you just need two values. One's the ADT of the major road, the other's the ADT of the minor road. It is not an entering volume calculation such as done for crash rate. Kansas DOT. How does the previous example mesh with consideration of regression to the mean? The answer is the elemental description for purposes of application of the Highway Safety Manual methodology today is just that. It's elemental. It does not, I did not include a rigorous EB analysis to account for regression of the mean. I gave you only one value for crashes. I didn't show you 5 or 6 years of crashes, and then we factor that to get the expected empirical base predicted number of crashes. That's rather long, it's mathematical, and really we would have eaten up most of the webinar with that calculation. So you can apply it. Today's webinar is a simple approach just to show the methodology. Robert Novi, how does the Safety Analyst Program use the HSM analysis? It may be the other way around, but let's describe to you. Safety Analyst is established for a state's crash reporting system tied to the state's roadway features for roadways and intersections and curves, should and is intended to give you the typical crash frequency results based on exposure for those conditions. Hopefully, you can use that information and then plug it back into your values that you use for SPF values and for crash modification values in applying the methodology of the HSM. Because so many states are just now getting underway with a rigorous safety analyst approach to managing their highway crash frequency tied to the roadway data, the majority of the states aren't able to do that yet. So the Highway Safety Manual, for the time being, until such time as the state has good, sound, rigorously solid results for performance of segments and intersections and curves, well, use the Highway Safety Manual values as your starting point for the time being. And that's a good way to relate how the two of them relate. Question from Sarah Wickland. So we can use the HSM for evaluating future new location roads, but then using traffic forecasts to determine the improvement to the safety based on reduction in AADT. I didn't cover anything on reduction of ADT. I'd like to know more about your question before I'll try and answer the rest of it here. Theretofore, providing quantitative information for use environmental impact with documents with safety improvements would be measurable. Yes, that is true. Prior to building a roadway, you could predict what the safety performance would be for the new facility that isn't built yet. And that's one of the values of the Highway Safety Manual. Got another question from Jason Osmond. When the highway design standards are in conflict with the HSM, which should prevail? It's not a case of being in conflict. Remember that the HSM is a set of analysis tools. It is not guidance. It is not standard. It's only a set of analysis tools. So hence there is no conflict, because inherent is that the design policies are the design policies. And the HSM doesn't change that. The HSM, just like the HCM, is just a set of analysis tools. It is not a standard by itself. In the case of a question posed I may have missed, how about freeways? Will the HSM predict collisions on freeways and use CMFs? And the answer is yes, there's a chapter on freeways. It will be strengthened in the next edition measurably. That is the one big gap and the one big thing that is the furthest behind in this first edition of the Highway Safety Manual, is that the known relationships for two-lane roads, for multi-lane roads, and for suburban urban arterials are strong, they're pervasive, they work well. But freeways, strangely enough, we just don't have the good solid knowledge to put them in as a chapter in Part C yet. They are in Part D. There is information in Part D, but it's not in Part C yet for predictive methods. The research is currently underway. It should be completed within a couple of years, which means it should be in the next edition of the Highway Safety Manual. Are there other questions that anyone has before we close out today's webinar?
I did have one question on the phone lines from Mr. Craig Copeland, I believe. Your line is open.
Thank you. I wanted to also talk a little bit about runoff road. You mentioned that those were real high incidence of collisions. So I guess you could use the safety manual to compare various shoulder widths through on a conventional road and arrive at shoulder widths that would be appropriate based on safety values for that particular roadway type and the ADTs that it has?
The answer is yes. The Highway Safety Manual in Chapter 10 rigorously gives the equations, and I in fact showed you a figure from one of the set of the equations for the effect of shoulder width and also the effect of a roadside hazard associated with the clear zone, objects in the clear zone, and side slopes.
Great, thank you.
Okay. Chase, are there other questions?
And I'm showing no further questions at this time.
I'm going to now move us over into the wrap-up room, and I'd like to call your attention to the webinar series presentations pod that's in the middle of your screen. You can download the presentations from today's webinars or the previous webinars if you'll scroll down. Also below that is the resources, the link to the Highway Safety Manual. In the upper right are links to the recorded sessions. We had a glitch on Tuesday's webinar on multi-lane urban-suburban intersections, and we're not able to record the session. We have scheduled and received confirmation that that recording of that session will be redone from scratch midday tomorrow. And as soon as it's completed, we'll post it as a link in the pod in the upper right so you can download it and view it if you'd like. The next webinar will be on rural intersections on Tuesday, June the 29th, and scheduled from 1:30. It says 1:30 a.m., but it really should be 1:30 p.m. To 3:30 p.m. Eastern Time. If that does nothing further, the other person's helping me says we still got some questions in the chat pod that we've missed. Let's see if I can go through and pick them out here. Let's see. Kansas DOT, can you explain why highways with higher excess crashes are more responsive to countermeasures? It would seem that just the locations that have a greater variance in the model. And the answer is actually a very simple one. If you look at crash frequency plotted year by year, and it changes. Each year is different because crashes are random events. When you're looking at locations that are high, remember that without any treatment, they may decline just under regression to the mean. Because they were a high value that year doesn't mean you'll have a high value the next year. And even if you make no improvement, you may see a reduction in crash frequency. So if you apply measures that actually affect crashes and reduce them, you will get the effect of the measure itself and also what is known as the effect of regression to the mean, in which there would have been fewer number of crashes just due to the random nature of crashes. And that's really what's at stake and why the phenomena that you questioned was an issue. Brian Byrne, to piggyback on Jason's questions, if the HSM says that an improvement is recommended by the highway design standards may actually increases, doesn't that imply some liability issues because we are making an improvement that research is showing it will actually increase crashes? Well, you want to look at the nature of the improvement and in your design decisions. I'll walk you through a very simple one. We know that putting a barrier closer to a roadway and putting it within the clear zone will increase crashes. And as we bring that barrier closer to the edge of the roadway, we see more crashes. All across America, states are installing something new. It's called cable median barrier to prevent severe median crossover crashes. The Highway Safety Manual predicts crash frequency for total crashes. So we would expect, and it's a reasonable outcome, and we know this happens from the experience of the state so far, as we install median cable guardrail, median cable barrier in the middle of freeways on the interstate and other expressways, we're seeing a good-sized increase in total crashes, but we're also getting exactly what we wanted, which was a reduction in severe crossover crashes. So yes, there are measures, as documented in the Highway Safety Manual, that increase crashes. But the Highway Safety Manual is not a standard. It is just a set of analysis tools that allow you to review your state standards and to make good decisions to change those design standards based on known safety performance. I hope that answered the question. If I need to help more, I'll be glad to. Question from Sony. I attended a workshop on low-cost safety some time back. Some of the tables are the same, and you're absolutely right. FHWA has consistently been deploying the same technology, particularly on roadside hazards and the known crash performance associated with roadside hazards in our low-cost safety improvements workshop for nearly 10 years now. Are there additional questions, Chase?
No further questions at this time.
I'd like to thank all of you for taking the time to participate in today's webinar. I hope you enjoyed it. And a little later this afternoon, we'll have the link to this recorded session posted in this webinar room for you to be